back.
Okay, let's get started here. So this is kind of another example to show you what the central limit theorem is doing. We have a distribution here with a very light skew. This is the single observations. This distribution up here is the distribution of single observations. What we want to now look at is when we take, I'm going to take like 1, 2 observations out of here and average them together and make one point in a new distribution of sample means of sample size 2. I could have taken 5, 1, 2, 3, 4, 5, and made one new point over here in this distribution of samples, in this distribution of means of sample size 5. If you notice, as we do this, increase the sample size for the distribution of means, the distribution gets more normal when you go to 2 to 5 to 10 to 20, and it also gets tighter. If you notice this bottom one down here, the scale, which was originally 28 to 44, is now 32 to 40. It's gotten a lot tighter, and also it's taking up less space. So with this in mind right here, what does this show us? We have a histogram that is originally skewed to the left, and these simulations appear to show us that with the central limit theorem, the mean, or the center of the distribution, stays approximately the same, while the shape of the distribution becomes more normal, and the variability decreases because it got tighter. Next, we have this theoretical question right here, and I'll work through part of it. It does kind of become redundant. With this in mind, it gives you the mean of the distribution as 36 point, and I can't read tonight, 36.35. If we were to do this for single observations, here's what we would have. Now, if we do it for, let's say, averaging together 2 observations, it'll stay the same. Think about this for a second. If you go outside and talk to one guy, you might expect him to be 70 inches tall, which is 5'10". Let's say you average together the height of 5 guys. What would you expect the average height of 5 guys to be? Well, besides burgers, man, I'm hungry. You would expect the average height of 5 guys to be 70 inches. As in, if the mean of this distribution of single observations is 36.35, then if we were to average together multiple observations and look at the distribution of means, then it would stay the same. It's not going to change. You expect one guy to be 70 inches tall, and you expect 20 guys to be 70 inches tall on average. So the distribution stays, or the center of the distribution stays the same. Okay, but what changes? What does change is the standard deviations in it. And the standard deviations for those distributions will be divided by the square root of n. So for this one down here at the bottom, dividing by the square root of n gets us, square root of n is 4.4, and the standard deviation is 3.95. So all I'm doing is taking 3.95, dividing by the square root of n. And if you notice, this number I have down here at the bottom is virtually identical to this one here in their simulation. Because they're doing this via simulation, kind of seeing what would happen, and we're getting the same numbers. Their mean stays the same just about. Their standard deviation gets smaller by a factor of the square root of n. And so these simulations are definitely showing us they are close. And let's look at this. Now I do have a problem with this, and you might get this answer wrong without this help video. But it seems to me that everything is normal around 10. We can zoom in here. That looks normal around 10. Let's look at this one. See, that looks to have a little bit of problems. But according to my Pearson, the all-knowing my Pearson, if we look at the completed problem, the answer is 5. And the original distribution was nearly unimodal and symmetric. It does have some skew, I know that, but because it's pretty normal to begin with, and let's take a look at it. The original distribution was pretty normal to begin with. And because of this, it's not going to take a very large sample size to make the distribution of means normal. And actually, this one right here looks much nicer than the ones I usually see for sample size 5. At sample size 10, it's very normal. The rule of thumb in this class is usually 15 works for small problems if it has a little bit of a skew, and 30 for kind of major problems, and 100 works for anything. But we kind of go by that rule of thumb. Okay, let's go on to the next problem. Here we're on the next problem. Now with this problem right here, let's go up. The GPA was an average of 3.5, and we expect the standard deviation to be 0.35. Now this problem is really great because we're taking sample size of 25. Now with this sample size of 25, that means when we get the new standard deviation for the distribution of means of sample size 25, we take the original standard deviation, 0.35, and divide it by the square root of 25, which is 5. And that is our new standard deviation for the distributions of means of sample size 25. This deals with taking college freshmen and all that good jazz. But there's a confusing part where people might get a little bit lost in here. We don't need that big of a sample size because the central limit theorem does not require that a distribution is normal. If we have a small sample size, it helps when it's normal because it'll normalize it. The bigger the sample size, the more normal it becomes when we do the distribution of means. So these people were, let's say, randomly and independently selected, which is basically just our random condition right now, and less than 10%, but it's not required that the distribution is normal. It has to be nearly normal. That is your third condition for quantitative data. And last but not least, we select the right distribution because the standard deviations are 0.07 here. We have it. Going on further, with this problem right here, this is the pregnancy problem. Now, I know I could work through this problem again. To heck with it, let's do it anyways. So here we go. We're going to go to the David M. Lane applet, our good buddy David M. Lane. And here's his applet. Okay, so we have women who have a pregnancy usually of 268 days with a standard deviation of 13. Let's go ahead here and put in 268 with standard deviation of 13. This is quantitative data. Always good to identify that within the problem. How long did your pregnancy last? 268 days. What percentage of pregnancies will last between 260 and 270? So let's zoom out a little bit. Between 260 and 270, we'll be just clicking here and doing between. Now I get a lot of questions, how would I do this on the test? You might have to graph it, that's a classic thing. If you notice, we're not doing the distribution of means here, we're doing right now single observations. So this is between 260 and 270, 29.2% right here. So 29.2% of the time this would occur. Next problem we have right here states at least how many days should be the longest 20% of pregnancies last. Now we're still doing single observations. If we want to see the longest 20% of pregnancies, as I copy over everything, if we want to see the longest 20% of pregnancies, we need to put this in here. And think before you hit the button. The longest 20% of pregnancies will be somewhere in between here and here. This is the top 16%, this is the top 50%, and like right here. That's according to the empirical rule. So about 279 days. That's how we get the longest 20% of individual pregnancies. Now what changes? The mean does not change when we go to a sample size of 30. Looking at the distribution of means of sample size 30, the mean will stay the same. We still expect 268 days. But the standard deviation will change to original standard deviation of 13 divided by square root of 30. And let's do this right here. Square root of 30. I cannot do anything right today, apparently. 30 square root, I did copy, and now 13 divided by the square root of 30, which I stored in there. So this is the new standard deviation for a sample size of 30. I'm going to go ahead and paste this into both areas on the chart right here. If you notice, the distribution got a lot tighter. So now when it asks questions, this is a distribution of means of sample size 30. I know I did not delete my decimals there. You will have to. Let's do it. What is the probability that the mean duration of these patients' pregnancies will be less than 264 days? I'm over here on this one right here, and I want to look below 264. It's somewhere right in here. So this is somewhere above 2.5 and less than 16. I estimate about 4%. 264, I say 4%. Ooh, 4.6. I was close today. That's got that problem out of the way. Okay, last problem. Okay, let's look at this last question right here. This last question right here is basically looking at a group of college freshmen and how many are retained. Now this changes the pace once again. The change right here is we're using the distribution of sample proportion. So with this in mind right here, we have 200 students and we expect 77% will be retained. Let's go ahead and use our calculator. Draw this out. We expect 77% at the center to be retained. We need to do P times Q over N square root to get the standard deviation. About 3%. So about 3, if this is 3 standard deviations, that makes it 9. So let's see here, trying to see, you see this has it way too tight. You can basically just look at it and tell. There we go, and you see there would be 68 right there. It looks confusing because it's not actually at 67, but that's the right answer right there. Now, this question is a good example of what we could put on the test. I really think it is, because it's tricky. Because it never says anything about the college students being randomly selected. That's the problem we have here on the test. It needs to say that things are randomly selected. A good test question will say, we randomly selected, and if it doesn't say that, do not assume it. To check the 10% condition, is 200 students less than 10% of all college freshman students? Yeah, sure, I believe that. Next, we need to check the success failure condition. We need to do 77%, or excuse me, let's do NP, NQ, the way we usually talk about it. And N is 200, and P is 77, that passes. N is 200, Q is 0.23, and both are greater than or equal to 10. That's all the conditions right there. This is a distribution of sample proportions, where these other ones were distributions of sample means. So make sure to do the right conditions and the right tests when you are doing this. This homework is good practice. It doesn't mean you know everything. Once again, there are other chapters on this test. Practice up. Email me questions. Good luck.
I wear my sunglasses at night so I can't bang my head